So you're now live on YouTube, and there goes the recording.
Oh wow.
Go ahead, Todd.
All right. So I threw together some slides for a Spack update. There's a lot going on, but I thought I'd focus on a few things. Um, I don't think I need to emphasize that Spack continues to grow. This year we're almost at 8,000 software packages, and we exceeded 1,300 contributors. And I think folks at this meeting are mostly familiar with this from the past. So there's that. I think that probably one of the more interesting things that I could talk about here is I'm going to talk a little bit about how we've become a Linux Foundation project, and then I'm going to talk about some technical stuff that's coming in the next version of Spack for ISC. So we've been thinking about becoming a Linux Foundation project for a while. I don't know if folks are familiar with this, but what that basically means is that we are Spack is no longer affiliated with just Livermore, who owned the trademark and so on. It's now got its own little 501c6 nonprofit company that's a legal entity for the project. And the cool thing about that is that it can be in legal agreements. We could have our own funding through Linux Foundation, and you can get discounts on things like Slack because now we're a nonprofit. And we have to have sort of formal neutral governance now. So we are in the process of setting up an initial technical steering committee. And the plan with that is probably going to be to make the main developer meetings more public, and also to have sort of official steering committee meetings. I'm not sure how we're going to balance between sort of the day-to-day technical work on the project, which is usually driven by consensus, and stuff that we actually have to have a vote on. But we're working on an initial governance MD, so expect that to sort of take form over the next couple of months. For Linux Foundation in particular, if you become a Linux Foundation project, you have to essentially donate the trademark for your project, which is sort of your license generally covers copyright and maybe patents if you're using a newer license like Apache or GPL3. But the trademark aspect of IP is not typically covered by that, but Linux Foundation actually covers that. So you have to donate your trademark, which is basically whatever stake you have in the name and logo, to the Linux Foundation, and they own that. And they have a pretty liberal usage policy. So like fair use is fine. You can put the logo on posters and stuff. What you can't do is create your own enterprise Spack and have it sort of compete with the main project. And the reason for that is really to prevent confusion. Just like you can't have like enterprise Kubernetes, you don't want like some corporate thing claiming to be the real Spack or the real whatever the project name is. They would have to rename if they wanted to do that. They can still fork, but they have to call the project something different. So like if you're familiar with like OpenShift, that's basically enterprise Kubernetes, but it's not called that. It's called OpenShift because that's Red Hat's brand. So this has been an interesting experience. The project resources are now owned by Linux Foundation too. So like the website, the GitHub organization, you add them as a co-owner. So in case the maintainers like go away, if we all get hit by a bus, Linux Foundation can still do something with the project resources and transfer it to new owners if that becomes necessary. This was something that we thought about for Spack. Because the project is scaling, we wanted to be able to have things like license agreements with other companies for distributing binaries. We wanted to be able to get our own Slack instance like some other folks have with like full history and so on. And we want to be able to buy things on behalf of the project and pay for things like user meetings. So I think it'll be helpful in that respect. But this sort of grew while we were doing it to become a larger umbrella foundation launch. So at ISC, we're also going to be announcing the official kickoff for the High Performance Software Foundation. And you guys may be interested in this because it's designed to be open for the HPC ecosystem. Essentially, under Linux Foundation, you can have these individual projects, but you can also have umbrella projects. So if you're familiar with Kubernetes or Cloud Native Computing Foundation, like OpenSSF, some of these other umbrellas, they are basically funded entities within the Linux Foundation that collect membership dues and other revenue for some set of open source projects. And we announced the intent to form at Supercomputing. We're going to officially kick this off at ISC. And there's going to be a BOF with more details on Monday, May 12th, or May 13th. So this is wrong. Let me fix that. May 13th at 1 p.m. So come to that at ISC. Initially, HPSF is going to be Spack and Cocos, and Amrex is an AMR framework from Berkeley Lab. Warpex is a physics application that's got collaborations from collaborators from Europe, like CEA, some of the national labs. I think some industry folks as well. Trilinos, you're probably familiar with. Aptainer, you may be familiar with. VTKM is an accelerated in situ viz package. HPC Toolkit is a performance tools package, and then E4S is the distro that ECP has made on top of Spack, and Charlie Cloud's a container framework. So this is the initial set of projects, but anyone can join. The prerequisite for being an HPSF is really just you need to be a Linux Foundation project. It's actually fairly simple to do that. Then you can be under the sort of the foundation umbrella. The initial members, at least is the way it's looking now, are going to be AWS, HPE, Livermore, and Sandia as like the premier members. We've got a number of general members, including NVIDIA, AMD, and Intel, so like the three major GPU makers, a number of the national labs, CEA, and Kitware. And then CSCS is likely to join as an associate member along with CDAC and the University of Oregon, maybe some other universities, we'll see. And the governance structure for this, if folks aren't familiar with how these projects are typically governed, there's a governing board that handles like the financial governance. So all these members are paying dues. You get some pot of money that you can use to sustain the projects. We can pay for things like CI or events, conferences, so on. There are various committees there that deal with things like marketing and promoting the projects. And then there's a technical advisory council, which is comprised of members of some of the projects. And so like we're sort of modeling the way that this works off of CNCF, where we haven't decided on what the names will be yet, but they have like sandbox, incubating, and graduated projects. Likely when we kick off, all the projects will be at like that incubating level. And the incubating and graduated projects would get spots on the TAC. So that's the Technical Advisory Council. They really coordinate the technical direction, the sort of shared focus areas that we want to look at for all the projects under HPSF. And then we would have working groups on things like CI, testing, software stacks. We want to do one on security, working with OpenSSF for things like supply chain security, working on like SALSA certified build environments for the stack, and so on. But really, I think this is going to take form more sort of after the official launch, once we have a budget, once we can decide what kind of activities we want to do. But this is what we're envisioning the structure to look like. So that's HPSF. And the goals with this are really to provide a neutral home for HPC projects. There are HPC projects that have foundations already. There was not an umbrella project for that that sort of enabled collaboration across projects in this foundation setting. And we wanted to engage more closely with industry. We had people like AMD asking, what's going to happen to Spack after ECP? And we're still funded through a different part of DOE, but people don't understand the sort of the way that the way that all the different funding sources work. And so I think for this, for stability of the project and for people to have trust in it in the long term, we're putting Spack into this HPSF and its own Linux Foundation project under that to put it in a familiar environment for companies to engage, for others to engage, to open up the governance, and to just give people confidence in the project for the long term. And really, that's not just for Spack, that's for all the projects in HPSF. And so the org will promote the use of these projects. Like we want to make sure that people know about them, that companies know that they can use some of these applications or frameworks like Cocos. We want to make sure that the software is accessible with CI, so we could pay for more CI with a budget like we would have under this. In addition to the donations and things that we get from companies already. We want to have these collaborations with other foundations like CNCF or things like containers and for running in the cloud, and with OpenSSF for security. And then also, I think we can sponsor training events and try to, really promote these packages among like new audiences and new communities. So that's the goal. it's really targeted at anything in the sort of HPC ecosystem, but also like high performance writ more broadly. We'd like to have some engagements with things like the AI community and and other parts of the scientific software community. So give us a look and come out to the BOF at ISC, or ask questions at the end of the talk. All right. So, or I guess what, any questions on that before I get on to the sort of more Spack part?
Any questions on the HPSF part, other than why the logo looks a lot like EasyBuild?
The logo doesn't look like EasyBuild.
No, I think we're good to continue, Todd.
Okay, cool. All right. So I think people here are familiar with Spack, but I always present these sort of 3 slides at the intro. There's really 3 parts of Spack that you want to think about. There's this syntax that you can use on the command line to install sort of arbitrary versions of things. So we have version specifiers. You can pick an arbitrary version of a package. We have compiler specifiers. You can pick what compiler version you want to build with. You can register a system compiler if you want to. Packages have options. You can inject flags into builds on the command line. And you can pick your microarchitecture target right on the command line. And all of that is recursive. So you can specify it for, say, mpitch or like some transitive dependency as well. This is how users specify what they want installed, both on the command line and in Spack environments. You can write a YAML file that says, here's all the things I want. Here's all my constraints, requirements, preferences, and so on. Those essentially drive our package recipes. And the package recipes are these Python classes that say, here, the homepage where you can download things, here are the versions that you could pick from. You can have variants and options on packages, and you can have dependencies on other packages. And they are, unlike EasyBuild, the dependencies are ranges. So, or they can be. You can depend on MPI. You could swap in really any MPI there. It doesn't have to be tied to a tool chain. You pick an MPI. You specify which MPI you want for an entire environment if you want to. And this says I depend on CMake 3.0 or higher. So you don't really have to rewrite this recipe. If you change your MPI, if you change your CMake, and so on. There's not a lot of tweaking required. And then the installation routines down here are really parameterized by whatever subset of this configuration Spack picks. And it has some default preferences, but users can set them as well. You're pretty free to tweak the way that you want your stack to be set up, so that it can, you can pick whatever your favorite version of script is. All of this is sort of tied together with what we call the concretizer. And so you've got these package.pys that are updated by users all the time, sort of a familiar way to, how easy configs are updated. But developers, users can provide preferences either on the command line or through different YAML files. And there's a ton of places where these preferences can come from. They all go into something called a concretizer, which underneath implements this logic solver. And its job is to spit out a fully qualified graph that we can actually build. So Spack is really constructing these the full build configuration on the fly. For 0.22 in May, we have a lot of updates, but I want to talk about 2 major ones. One of them is compilers dependencies. We're not going to have the whole thing done for May, but we have made a lot of progress on that. And so I'm going to talk about some of the additions to the stack that have gone in for May. And then the other one is the way that we're supporting the Python ecosystem. We're moving from a model where we take every Python package update, like a new version or new dependencies, new constraints as a pull request and iterate on it, to a model where we would auto-generate most of the Python ecosystem. And so I'm going to talk about this one last. Both of these rely on some solver features that we got in for our last release in November. And they have been a long time in the works. So just for reference for folks, the concretizer itself is built on this language called answer set programming. If you're a user of Spack, you never have to see this. But all the inferences that are made to adhere to the preferences in the solver all of the decisions for how dependencies get set up and how we deal with version constraints, variant constraints, dependencies on particular versions or variants, and so on, is done in ASP. And just at a very high level, you might have some facts that look like this, like node lamps, node CUDA. That means lamps and CUDA are in the graph. Variant value lamps CUDA true. That means the CUDA variant on lamps is set to true, and depends on lamps CUDA means lamps actually depends on CUDA. If you have facts like this, we can have rules that look like this that basically infer things from the facts. So if you have node HDF5 and HDF5 depends on MPI, we can deduce that MPI has to be in the graph. And then we can further deduce that we have to pick like an implementation of MPI, we have to pick a preferred implementation of MPI. It might end up being open MPI, it might end up being your system one if you've configured Spack that way. But this is how the solver is making decisions. And so inside the solver, we do something called grounding, where we take, say, a propositional program like this that has some facts, maybe some first order rules, and some choices. And we do something called grounding that, which basically converts the whole program into something without rules. We basically explode all of the rules that have variables in them with all the possible instantiations of those rules. And so you end up with these sort of concrete rules where it says like node A implies that node B is also in the graph, and so on. And then finally, that implies that there may be like two possible solutions to this graph or this graph, and we have to pick the one that best matches preferences. So that's how these things are implemented underneath. And we're using Klingo from the Patasco group at the University of Potsdam to do this. But that's basically how we've made this general solver. The problem sizes for Spack are pretty large. And the main logic program is around 250 rules with 20 different optimization criteria. So we're doing some multi-objective optimization, and it's like around 1,000 lines of ASP code at this point. The size of the problems can get pretty big depending on what package it is. So I think the only package in Spack, or one of the only ones, that doesn't actually have a bunch of potential optional dependencies at this point is GNU config. And most other things, like say zlib, actually have a lot of possible dependencies because gmake has an optional dependency on guile, I think, or scheme, some Lisp. And so 500-ish possible dependencies is kind of normal for the solver to consider. When you create the logic program for that, it can range from anywhere from like say 30,000 facts up to like 300,000 facts for some of the bigger applications, depending on how many dependencies have to be in the graph. And then we go and solve that. Then we take those facts and we ground them with all the rules that we have, and that can be even bigger. And so the solver is doing this hard thing to solve actual SAT problems on these rules. One of the things that we spent a very long time trying to get to work that was critical for compiler depths and for Python is that originally Spack basically said, you can have lots of different graphs installed. You can have 16 versions of MPI, but within any graph for that MPI, you can't have two versions of the same package. And that's sort of true. You can't have two versions of something loaded at runtime in Python, and you can't have, say, two versions of zlib loaded at the same time in a C program in a process, because they will just cause a loader race, and you'll get bad things will happen if you end up calling ABI incompatible routines from one or the other of them, or just one will win if they happen to work well together. But you can have different versions of build dependencies in a graph. Essentially, every node in the graph has its own environment for building, and one node could have one version of a build dependency, and one node could have another version of a build dependency. Well, we didn't support that, and so for things like gptune here, where you have it depends on PyG event, NumPy. One of these depends on an extremely old version of Python, which is just a build dependency. It generates some code. And the other one depends on a newer version, or a recent versions depend on a newer version of Python. And so what would happen is we would have to choose a really old version of PyG event to make it compatible with the version of Python required by NumPy, which is fairly old. And this is bad because it basically means that we're forcing certain packages to have old versions in the Python ecosystem frequently, and we don't really want to do that. So we spent a lot of time adding this concept of unification sets to the solver, and essentially what that means is that we have this circle here where we can have one version of any dependency, but outside of it, we could have multiple versions of things. So PyGEvent has a build dependency on Python. That's fine. We'll use version 3.0 for it in its build environment, and it's never used again. And then NumPy has a dependency on Python. We'll use version 0.29 for it. And this is fine. Like this works. This is how you want to compile this thing. And the Python ecosystem does assume that you can do this all over the place. People really, really like to pin versions of build dependencies in the Python ecosystem. And so it took us a while to do this properly. We had to make it so that we could split nodes essentially when we needed to. So that certain nodes that were, their build dependencies, they can say, I could have multiple versions of this. I don't necessarily have to. I'd rather have one version of this thing. But if I have to, in order to prevent something else bad from happening, I can do that. So we added some rules to the solver where we, instead of having an identifier for the node that was just the name, we now have an identifier for the node that's basically an ID and the name. So the solver can sort of create new versions of a particular node on the fly as it needs to. We had to generify the package metadata so that essentially, like when we include a package in the solve, we can duplicate it as well. And so we would have, we have just one set of package facts that describe how a package should behave. But if we end up having a second node for something, then we can consider the same set of package facts for that new identifier that we came up with. When we first did this, we blew up our solve time to the point where things were taking minutes to concretize in some cases. And that's not great because it makes the tool not very usable. We went through and did some profiling on the solver and found that a lot of the logic that we were using to do things like transitive paths, where like we were sort of computing all of the possible paths in the graph, were quite expensive. And so we took out some of this. We learned a little more about Klingo and found actually a hidden feature in Klingo that the developers told us about, where we could do cycle detection natively in the solver. We wouldn't have to model it ourselves. So that was quite helpful and helps to get us back, to the sort of same performance regime we were at before. One of the other problems we ran into is that a naive implementation of this sort of build dependency splitting, where you say that you could have a separate dependency environment for essentially every build environment, is that if you follow the transitive closure of that, if you look at every node in the graph and say every node could have potentially many build environments, and each of the things in those build environments could have their own different build environments, the solver has to construct this exponentially large set of possible scenarios for all of the different unification sets to consider. And so we had to break the recursion there to avoid that sort of blow up. And we allow deviation to an extent within the solve, but we bound it, for transitive build dependencies. And so most of those are thrown into sort of a common unification set, but we allow splitting of nodes at the sort of immediate build dependency level on the graph. And this seems like it's enough for Python. We're now able to concretize things, potentially 5 versions of setup tools that are very specifically bound for different nodes in the graph. And that's made handling the Python ecosystem quite a bit easier. We also had, a number of optimizations that basically got us back down to, good solve times from the first implementation, including, the cycle detection thing I talked about, optimizing unification sets, optimizing some of our variant propagation logic, which used the same sort of transitive rules. And then finally, Harman went in and optimized the Klingo binaries themselves and added things like PGO to our bootstrap binaries for the solver to where it's quite fast now. Wasn't trivial to come up with this. I think there were like 4 or 5 attempts before for approaches that didn't quite work, or that would put burdens on the packagers to think about these details, and that weren't nearly as automatic as what we actually came up with. So I think in all, like, we've been trying to do this for like 5 years, and finally came up with a way to do it in the solver that scaled well. So we're pretty happy. And that's enabled us to do some work on both compiler dependencies and on the Python ecosystem itself. So I'll talk about that. We've wanted to have compilers as dependencies in Spack for a long time. Right now, in the current version, if you set up your compilers, you have to do it in a config file. The compilers are sort of their own special entity, like outside the dependency graph. And that means that we can't model all the pieces of the compilers that we'd like to in order to understand compatibility. In most systems, like say CMake or in like EasyBuild, you generally have to choose a tool chain in advance and choose a set of compilers, and then those decisions are made. You cannot revise them or really incorporate them into the dependency model. And that's sort of how it's been with Spack, where you have to choose compilers in this config file off to the side. With this, we are really making compilers proper packages in Spack, which has involved creating sort of new types of dependencies and modeling the runtime libraries. And we're really trying to do this to make it easy to install, say, an arbitrary GCC version from, say, a build cache, and also to properly model compatibility for compiler interop. So like one of the things that we want to be able to do on the El Capitan system at Livermore is we'd like to be able to compile an executable that uses the Cray compilers and the AMD compilers and GCC all together, and to know exactly how we should link that depending on the compatibility of the runtime libraries underneath those compilers. It can get really complicated if you consider things like OpenMP, because there are different ABI bindings in the various libraries there. So we made a lot of progress, and the first thing that we've done is compilers in Spack are now associated with the package that models them. So like we have this concept of a GCC compiler. We still are modeling it as this compiler object, but it's associated with the actual GCC package in Spack. So a packager can add extra logic to the GCC package to do things like inject runtime libraries into the build. So what that means practically is that if you end up using GCC as your compiler, Spack will query this new sort of runtime constraints method in the GCC package that says, hey, so I'm building with you. What runtime libraries do I need to model in order to have a GCC build of something? And so we have this syntax in Spack now that allows you to, using essentially the same syntax that we use in the package, inject kind of global rules into the solver. And what's cool about that is that you can say that every package, if it depends on GCC, also depends on this GCC runtime node. And so you have like an interface, which is like, I want to build with C and I'm using the C compiler. But the compiler class itself provides the implementation details for how the runtime ought to be modeled. And it could do that in lots of different ways, and different compilers do. And so you've got a GCC runtime here. This is like a very abbreviated version of what's in the GCC package. We also have Fortran runtimes in there now to model sort of libg Fortran separately, so that it can be handled separately when we build with like the Intel compiler, which has libif core and some other Fortran runtime trickiness. And so this has worked pretty well. It's a very concise way to describe the runtime dependencies you want, and it allows us to get graphs that actually have the runtime nodes in them. Effectively, what that means is that when we build things in Spack now, the libstd C++ dependency that the packages have is unified properly through the graph. So we could have different compilers hanging off of different nodes with our split build dependencies thing that we built for Python and for this. But those compilers have to choose a runtime library for compatibility, and we can enforce that the libstd C++ for one build is in fact compatible with the libstd C++ for another. It's likely that the GCC runtime node is going to get split out into more and more things over time as more of these sort of compatibility issues come up. But the cool thing is that it's now on the packager to do that. And so whoever's maintaining the GCC package, which is probably us, but can now express these things to Spack. The other thing this does that is super useful is it allows us to put packages built with much newer versions of GCC into a build cache. And so we can build a binary that's built with a libstd C++ that's way newer than what's on the system. And the GCC runtime package itself is actually a copy of the runtime components of GCC. So we build that dynamically. And that if that gets put into a build cache and you install some packages from that build cache that need a newer GCC runtime, you get the runtime libraries, and the RPaths point to them, and so the package works. You can basically package arbitrary compiler versions now, and their runtime libraries will be installed with the binaries. So this makes for some pretty smooth integration there. The other thing that we're doing is packages can now declare the languages that they depend on. So historically, like because we had to pick the toolchain in advance, we had this implicit assumption in Spack that everything was building with a C compiler, a C++ compiler, and a Fortran compiler. Well, not all packages are doing that, especially not like Python packages. And that also made interop hard. If you want to do mixed compilers, you would have to put a compiler definition in that like says it's Clang, but actually uses, say, XL or some other compiler behind the scenes, or Intel for Fortran. We don't have to do that anymore. We can have separate compilers satisfying the C++ and Fortran virtual dependencies. And so for the packager of, like, say, a normal package, all you do is you say, I depend on C++ and I depend on Fortran as the build dependency. And then, again, behind the scenes, that gets resolved into, say, GCC as the C++ provider or the Fortran compiler. And then the compiler says, here are the runtime libraries that you also need to add. And so we've really sort of abstracted this language interface in the package ecosystem so that we can sort of change compilers underneath and also have the runtime libraries modeled. This isn't a virtual dependency the way that we model it elsewhere in Spack yet. It's sort of specially handled until we really move the compilers to be proper nodes in the graph. But we're on the way, and I think this has improved things quite a bit. The other thing we did is we added libc as a dependency, and so this went in recently. Harman did this. I think he's actually on the call. And libc is now a virtual, and glibc and muscle can provide it. So we could build a muscle-based Spack stack using this if we wanted to. We could build, like, from our own libc from the ground up. Nearly every graph has libc in it via the compiler because you need it for to implement the C language. And libc is fundamental for binary compatibility on at least Linux, but pretty much on every other system too, although the implementation varies. We are not building libc because I think our users would murder us if we built libc for every build that we did in Spack. What we are doing is there's libc detection in Spack now. So if you build with a compiler, we query the compiler, we say, hey, what libc are you actually using? And then we go examine the libc to figure out what version is it, and what metadata should we put on our libc node that sort of gets injected into the graph. And so now, with every node, every build in Spack having this libc node, we are much better able to evaluate the compatibility of binaries, because we can know, for example, that like something built on CentOS that has an older version of libc that's compatible with, say, the one on Ubuntu could be installed on Ubuntu and used just fine. This is something that's done very frequently in like the Python ecosystem. So like the many Linux spec sort of outlines how to build a portable binary with an old distro so that it has an old libc. We're essentially putting the metadata into the graph so that we can evaluate the binary compatibility ourselves. And so this has helped build caches as well. If you check out Spack Develop right now and you point to our sort of what we're calling like our generic build cache, which I guess if you've been hearing easy updates here, you could think of that as kind of like the compatibility layer in easy. We can get a lot of build cache hits for like the lower level dependencies that people don't care about building in a fancy way by using this. So if you try to install Emacs, like most of the tiny things that it requires at the sort of leaves of the dependency graph get installed from CentOS builds, if you point at that. I think what we would like to have by, say, November is for Spack to have a build cache on by default, so that for most builds, you get most things satisfied by portable binaries that are maybe optimized for like x86 64 v3, right? Which is still like AVX256, like it's still pretty good. And then, if you want to build your application or something specifically for the machine, you can build that on top very easily, leveraging this functionality. All right, and finally, managing Python packages in Spack has become pretty unwieldy for a lot of reasons that I already mentioned. Like there's lots of small packages. The developers in the PyPI ecosystem tend to overconstrain their dependencies, like especially for build dependencies. They don't want to provide ranges for those. They just want to say, like, for this build environment, we want to build this. And this had gotten to be a problem because it's a lot of work to maintain all the pull requests. We had Adam Stewart doing that for the whole Python ecosystem for a very long time. And he's, actually become busy now that he actually got his PhD somehow, despite working on Spack. I don't know how he did it, but he did it. It's very impressive. But now he wants to move on and just maintain the machine learning ecosystem. And with him being busy and moving on from Python, we started rethinking how we would maintain Python packages in Spack, and so we decided to automate this. And so Harman has put together a tool that can actually generate pure Python packages. And the idea is that we will use PyPI's metadata. So they have this Google big table database with a lot of metadata about like the wheels that are in the PyPI ecosystem. We're going to use that for the pure Python packages, the ones that really don't have a platform or any native code associated with them, that essentially if you install the wheel, you're installing the source just as you would intend to, or just as Spack would do if it tried to build it. For any package that requires native builds, we want to continue modeling those as proper Spack packages and basically overlaying them on top of the underlying Python stack. So Harman has put together this tool called PyPI to Spack package that goes and queries PyPI. It looks like this. You can basically run, generate something from some requirements, and it will spit out a Python package that has version constraints as they appear in PyPI, but pruned somewhat. We don't want to include all the metadata because there's like tons of metadata on PyPI. So Harman has come up with a lot of useful ways to prune the metadata down and to make it tractable, to merge constraints where it makes sense, so that like our version ranges are sort of the combined version ranges from PyPI expressed in a more, Spacky way, as opposed to having a completely constrained sort of version dependency. And then he's also added some support to our versioning system so that we can handle some of the more frequently used semantics in the PyPI versioning schema. So like they use pre-releases, alpha, beta, and RC releases very frequently, and we didn't really have proper support for that in Spack. And so now those are compared properly in our version system, and we're able to generate versions that have those attributes and have them function properly. So this is new. There is a big PR that Harman has put in from auto-generated Python packages that moves us pretty much for all of the pure Python packages from SDIST, which are you check out the repo and build the Python package from straight from source with all the build tools, to wheels. And I think this will make the Python installations way faster. It'll make it easier to manage the ecosystem because we'll be tracking pipeline more closely. Caveat is really that wheels don't have build dependency info. They are, the Python people call them binary packages, which I think is kind of funny because they're just Python source. They're not really binaries. But in the sense that you don't have to build them, and if there's any code generation or other sort of preparation that's required for making a release, the wheels basically include all that already. And so if you wanted to use Spack develop on one of these, it's probably not going to be what you expect. It's not going to look like a source checkout that you can then go and build, and we don't actually know the build dependency information. So for the ones that we do want to develop that way, we'll have to go and add that stuff ourselves. We'll have to go and add ways to check out, say, the actual repo, as opposed to the wheel. But for the majority of the Python ecosystem, I think this is improvement because, we cannot maintain it ourselves. It's a whole other evolving ecosystem, and I think this auto generation will help a lot. So that's where we're at. And so, summary: HPSF is kicking off in May. Spack is in it, along with a number of other projects. It's part of Linux Foundation. If folks are interested in joining that, or getting involved, let me know. You don't have to join as either a project or a member to participate in, say, the working groups or the projects. It's open. The split build dependency work enabled us to do a lot of work around compiler dependencies. What we're missing and what we're probably going to have for an SC release like later in November is making the compilers proper nodes in the graph. We're not quite there yet, but we have this association between Spack compilers and the actual compiler packages. We can inject runtime libraries, and we have a lot more compatibility support now that enables us to do way more with build caches. And Python package generation is something that's going to go in. So any questions? Can folks hear me?
Yeah. Okay. Sorry. Thank you, Todd. Um, yeah, time-wise, well, we're way over time already, but I think we can take some questions if people have some. I definitely have one or two, but if somebody else has a
I'm
question,
shocked.
yeah.
A very simple questions. In the past, I think we were related to a singularity, the singularity company. Is it still the case or is it done?
Uh, sorry, you're asking me if I'm related to the singularity
Me
or
or Spack? I mean, I thought there was a relation between Spack and singularity, but maybe I was misunderstanding.
only in the sense that Max used to work at Scilabs. So he was for a year. We were sort of contracting with him through Scilabs, but when Greg left and that whole split happened, we've been contracting Max directly. He set up his own company and he works for us via Livermore now, not via Scilabs.
Okay, thanks.
Yeah, sure.
Other questions for Todd? If you can go back a couple of slides when you mentioned adding libc as a, what was it, the proper dependency or yeah, this one. So here are you only looking at the version of libc that's provided by the OS, and is that specific enough? Because like Red Hat probably backports a ton of patches and they keep calling it the same libc version, but it's really not.
Yeah, that's right. So we still have the OS tag on those. Likely we will get rid of the OS tag on everything built by Spack itself, but we'll keep it for externals. And so for a Red Hat libc, it would basically be glibc at 2.31 with, and you can't see it here, but there's like an OS equals over on the other side. Okay. So we'd have the actual distro associated with that. How that would factor into compatibility rules, like someone would have to go in and say like, when it's the Red Hat version and when it's at this version, it actually means that it's compatible with this, right? Like, so we'd have to maintain rules for that, but yeah, we could model that.
Yeah, because if I understand it correctly, glibc is currently not in the Spack build cache at all, right? You're always relying on the OS.
That's right.
Yeah.
Sort of.
Doesn't that mean if you ship binaries in the build cache that depend on, let's say, glibc 2.31, that you're not really 100% sure that's actually going to work on another OS that provides a compatible...
You'll only install on an OS that has like a newer version of libc, or equal or newer version of libc currently.
But is that enough of a guarantee that it will actually work in practice? Might there not be cases where stuff has been backported that the binary actually depends on? And then for let's say if you have that you're building on CentOS 7, and then you copy the binary to Ubuntu version that has a higher libc, but there may be cases where that's actually not really working in practice, I think. Depending on how heavily... I have not seen
that happen. Okay. So CentOS 7, at least, and I mean, we don't have to, so what I was getting to is actually that we don't have to use the distro libc. And in fact, here, let me see if I can, yeah. So PR here. We actually have a prototype self-hosted Spack now.
Okay.
Where we wouldn't actually require any host libc to build. And so Tom has built like a glibc GCC bootstrap sequence with a couple environments. We're still working on how that would map to like an actual bootstrapped dependency model, but we're able to build a pure Spack container that has a Spack libc and absolutely nothing that's not built by Spack in it. And so if we want to stick to like pure libc, we could do it this way, or pure muscle, right? Like we could have our own Spack OS container for those things. This is not merged yet, and I think it's going to need some syncing with the work that's happened since. But it is, I think eventually what we'd like to do is have everything in the build cache built with our own stuff, as opposed to relying on the libc from a container. The reason that we chose CentOS 7 is because the many Linux standard chose that. And the Python wheels tend to be pretty broadly compatible. I haven't seen them, screw up in major. Well, I can't say that I haven't seen them screw up in major ways, but it wasn't because of the libc; it's because of the wheel. So, yeah. Does that answer your question?
Yeah, more or less. Yeah, and cool. I'm wondering if there's any significant performance impact in doing that as well. But I guess if you're building your own libc, you're not really going to be stuck to an older version.
Nah, we could build newer versions, and in fact, like many Linux continues to move forward. It wouldn't be like Condo where they're stuck on some absolutely ancient libc version.
Yeah.
We can decide that at a particular point we want to have the build cache stack, support a newer min libc version or a new new min muscle version or whatever. Yeah. And the question really for maintaining the build cache in that case is like, do you build the whole thing with the really old version and have broad compatibility, or do you start splitting and have the concretizer resolve the compatibility of the binary with the host system, right?
Yeah.
And so it's like, how much do you want to build? Is really the question. How much specialization do you want?
I guess going forward, it will become more of an issue to maintain the build cache, just because things like ARM become relevant, and eventually maybe RISC-V as well. So that's definitely going to explode your build cache quite a bit as well.
Yeah, I mean, I didn't talk about it here, but we have done a lot of work to scale the build cache. So I mean, I think currently we have like around 8,000 packages that are being built in there, and they're aggressively cached, and they're built essentially on every PR. We have, and that has gotten slow. One of the things that we're doing that I didn't talk about here is we've got a PR that lets you basically include another environment concretely. And essentially what that means is, like, previously you can include config, right? And you could reconcretize the whole thing. This basically says, I'm making an environment. I want to include the lock file from another environment. And so likely what we're going to do is stratify the build cache. We already have like a dev tools stack that's built on CentOS 7 that has a bunch of like the sort of lower level like build tools that you need for like your basic Unix stack. Likely all the other stacks would include that one. We have different stacks that include Rockham in different ways right now. And what we want to do is consolidate the Rockham stack, or at least consolidate like several Rockham stacks for different Rockham versions, and have those included concrete and other things. And so really, like, we want to isolate where we are maintaining the binaries for particular parts of the ecosystem, and have at least some reasonable set of versions for things, but not everything, and not just completely freeform. And so I think once we do that, the build cache becomes easier to maintain, and testing becomes easier because the sort of surface is constrained. But the cool thing is that, like, you could include that. You could get a lot of hits on the default build cache. But if you wanted to change something locally, the solver will go and like build what you asked it to and reuse as much as it can from the build cache stack. So that's kind of where we want to get, where like you're mostly on Rails, but you can deviate in useful ways smoothly. Does that make sense?
Okay, yeah. Any more questions? Okay, I think we're ready to wrap up. Thank you very much, Todd. This worked out really well, I think. And we're always happy to have you. You know that. If you ever do end up doing a Spack user meeting, make sure you invite me as well.
I would like to plan one, hopefully for August, but we're kind of waiting for the funding aspect of HPSF to kick off before we do it. So yeah, I'll keep you posted.
Yeah. All right. Thanks a lot.
All right. Awesome. Thanks.
All right.